Lesson 4.7 Optimization Problems. This lesson is using our previous knowledge on how to find an absolute extrema on an interval and applying these to word problems. These word problems are almost always how to optimize an area, a surface area, a volume, depending on the example you're using. There are about 5 steps to solving an optimization problem. We're going to use this very simple example and in order to show how to use these 5 steps and apply them to other problems in the future. Our example is a cardboard sheet is 20 by 30 inches. In order to make a box, a square must be cut out of each corner. How big must a square be in order to have the largest box? So our first step is to draw. This is the most important step because we have to understand how we want to set up the equation and visualize everything in order to understand the problem the best as possible. So a cardboard sheet is 20 by 30. So we're going to draw this cardboard sheet right here. And this side here will be 20, and this side here will be 30. Now we're going to cut a square out of each corner like this. And since we're trying to find the size of the square, we will have to set each side equal to x. So there's x right there. Now, this sheet is going to be folded up into a box, and that's going to look like this. Once these squares are cut out. And this side here, and this side here, we're going to solve for the sides algebraically. So this side right here is 20, and if you take away these two boxes here, it'll be 20 minus 2x. Same for this side, which will be 30 minus 2x. And the height here will be x because of the square we cut out. Okay? And then our second step is to understand what we are maximizing. In this problem, we can see we have to make the largest box. And that means our volume has to be maximized. So we have to have the largest volume. And so we're going to make an equation for the volume using the things we've already done. So the volume will be length times width times height. So it would be x times 20 minus 2x times 30 minus 2x. Now, the third step is we have to find the constraint. And that is the interval that we're finding our absolute minimum and our absolute maximum. And so we have to look at this problem and understand what our interval is. So x, obviously the smallest x can be has to be 0. And if x is 0 in this situation, the box will be a flat surface, but it will still be considered possible. And the largest x can be, if we have to look at this, if we have 2 x's on one side, and since 20 is the smallest side, we have to look at that. If we have 2 x's on one side, that means the largest x can be is 10, which means that this entire side would be cut out if each box was 10 by 10. And so that is our constraint. And then the fourth step is to find the critical numbers. And in this step, we're finding our absolute maximum and absolute minimum. So we're going to factor out our volume, and that will give us 4x cubed minus 100x squared plus 600x. And then we're going to find the derivative. The critical number is setting the derivative equal to 0. So the derivative of the volume would be 12x squared minus 200x plus 600. Now if we set that equal to 0, we can plug that into the quadratic formula because it doesn't factor out very cleanly. So get 200 plus or minus 4,000 minus 4 times 12 times 600 all over 24. Now, if we plug that into a calculator, we will get x equals 12.74, or we get x equals 3.92. And obviously, x cannot be 12.74 because it is larger than 10 in our interval here, so that would be crossed out. So our critical number, and our only critical number, is 3.92. Now, our final step here is to test our endpoints. Because when we're finding a relative maximum or minimum, not relative, an absolute maximum or minimum on an interval, it can be one of the endpoints. And so we have to test the endpoints, and here in our interval, we're already given our endpoints. So if x equals 0, then our volume here has to be 0. And then we have x equals 3.92, and that gives us our volume, which would be, if you plug that into a calculator, 1056.3. And then if our x is equal to 10, which is our endpoint here, our volume has to be 0 because 20 minus 20 equals 0. And now we can see that this obviously is our maximum. And we could see this by using the second derivative rule. A more clearer picture of it can be given by the second derivative rule, and that's 24x minus 200. That's the second derivative of our volume equation here. And the second derivative of our critical number here gives us a negative number, which means that our graph is concave down, like this. And so you can obviously see that here would be our number, and this would give us our maximum. This would be our maximum volume. That's what we're doing. We're maximizing the volume. And that's what it gives us. And so then we have to create a sentence. So the largest volume of the box is 156.3 inches cubed when x is equal to 3.92. And that is our answer right there.